Right, well, I'm now going to introduce Steve Greb from GeoAquaWatch, who's going to talk to us about the global perspective and future opportunities. Okay, thank you very much, Steve.
Well, thank you, and thank you for the opportunity to talk with all of you today a little bit about GeoAquaWatch and some of our activities. I mean, I see this session was called Future Development, and I would say we've been hearing about some of the cutting edge work in the future in some of the past few talks here and past few days by some of the top experts in this field. Many of which are part of AquaWatch, by the way, are members of the AquaWatch community. So it's been great to hear, and I think, as I said, you've heard a little bit about the future from these past speakers. So in some essence, the future is now. So I'm going to talk a little bit, again, as I said, about the GeoAquaWatch initiative. We would be considered a community of practice, if you will, and we fall under the GEO umbrella. For those of you who don't know what GEO is, it's the Group on Earth Observations. It's a large organization consisting of over 100 member countries and many more NGOs, intergovernmental organizations, people from the private sector, all coming together to, as it says here, improve the availability, access, and use of Earth observations for the benefit of society. GEO is organized into 9 societal benefit areas. We would fall under the water benefit area within the GEO umbrella. So drilling down a little bit, GeoAquaWatch, our organization has the goal of, we're here to support the water resources management, decision makers, citizens, the private sector, any number of our end users by helping to develop and build the global capacity and the utility of Earth observation derived water quality data, products, and information. So what's the drive of AquaWatch? What's our impetus? We all know clean water is critical for human and ecosystem health. It's, of course, important for our security and economic growth. We have seen waterborne diseases is still one of the most significant threats to human health worldwide. The World Health Organization estimates 1.7 million humans die a year. And it may not be a fair comparison or a little bit of apples and oranges, but just looking at the coronavirus yesterday, world numbers are a little over 1 million deaths. So this is on the same order of magnitude, and I guess points to the severity of this problem and the concerns we have for this issue. Water quality is, the status is quite variable and reflects, as it says here, the social economic factors within a country, as well as the physical factors, the geography, and development pressures. It's always been our premise that monitoring is a critical first step for proper management, and so that's one of our main thrusts is to improve our ability to monitor water quality around the globe, and this helps make management transparent and sustainable. We do know that, and has been pointed out by some of the previous speakers, that many regions of the world lack the resources for systematic monitoring. Well, one of the reasons that AquaWatch has gotten involved and interested in satellite remote sensing in particular is because of the new and improved sensor technology, the novel algorithm developments. And again, we've heard about some of this over the past few days, as well as the image availability, increasing accessibility to these imagery and the processing capabilities. So there's been some major advancements in satellite remote sensing of inland and coastal waters. The other thing that we like from a global perspective is the satellite imagery is not restricted by the political borders. We're not just looking at what the water quality is on one side of the river versus the other side. We are taking a more holistic approach and looking at watershed, taking a watershed perspective. And one of the things that has really attracted us, again, because of this could be useful for monitoring data gaps, previously undersampled, or in many cases never sampled, or hard to access areas. And again, we heard about that a little bit this morning from Claire. And I also want to point out, as Stefan mentioned, I don't want to oversell satellite remote sensing. We see it as a tool, one of the tools in the toolbox. But in cases such as some of these remote areas in developing countries where there just is no data, this is a good alternative and something that I think we'll see more of in the future years. Just one slide about the AquaWatch, our organizational model. The 5 dark red circles here are our 5 components of AquaWatch. They're backed up by 5 working groups, and they address our 5 objectives. Starting on the top with outreach and end user engagement, understanding what are the needs of the end user. Going down the right side, observation and data, look everything from satellite sensors to, again, the data and data processing, to the products and information that are of interest to the end user, to the distribution, access, and visualization, getting this information out there so it can be used. And finally, education and capacity building, which is an important component of our effort. All this feeds into what we call our water quality information service. So today I want to talk just a few minutes about some 5 different activities that we have ongoing now. The first one being analysis ready data, or what's termed ARD. I won't go through all this, but just to explain it briefly, yesterday, Karsten in his talk did a little primer on remote sensing and talked about the water being a small portion of the satellite signal, that there's many interferences from things like aerosol, sun glint, clouds, land adjacency effects. And this ARD activity essentially is doing a lot of the heavy lifting, if you will, a cleaning up of the data to, as it says here, to reduce the burden, particularly for the inexperienced data user. We think this will promote data quality and consistency with some specifications we have, and also enable improved interoperability due to consistent specifications across different data sets in time. And this would be important, particularly in terms of the climate change initiative, which we've just heard about. The second activity I want to talk about is compiling existing data sets. This is a project which was just funded this past year, using on campus here at University of Wisconsin, the Real Earth portal, in attempts to bring together data of varying file formats, naming conventions, columns, and transforming it into one cohesive data set, the integration of these data sets. And we're bringing together grab samples, buoy data, satellite products, and putting this all in, again, a common database and a visualization tool in which you can, again, display the data, look at time series, scroll across to look at data comparisons, so you can start understanding some of the differences and between some, say, the remote sense derived data and the in situ data. This will be embedded within the AquaWatch website and linked to the Geo system of systems, and will be updated hourly. The third project, and now we're moving from compiling existing data into generating new data sets. This is a project we're pretty excited about that was kicked off late this summer. It's a Google Earth Engine project. This is a collaborative effort between GeoAquaWatch, the World Bank, Conservation International, UNESCO, and Google Earth Engine. And the goal of this project essentially is setting the foundation for the Water Quality Information Service that I initially talked about, was to provide this global scale, open access, freely available, fit for purpose for these three parameters, chlorophyll, TSS, and CDOM, water quality information for inland and coastal waters to be used by multiple end users, including the science community, water resource managers, industry, and the general public. So there's a lot in that that goal. It's an ambitious goal, as many of the participants have expressed. We're just in kind of the kickoff phase of this project. One of our first steps was bringing together a number, and at this point it's roughly 20 people who have expertise in algorithm development to help us come up with an algorithmic strategy to address this, the global nature of this project. So stay tuned, you'll be hearing more on this in the future. The fourth project I want to mention, and I should have said early on that you know, the theme I wanted to stress today was strength and confidence in Earth observation and water quality data. And again, this has been touched on by some of the previous speakers, particularly today. But the fourth project is on validation. Validation is a huge issue in the satellite remote sensing water quality world. It's something that's talked about a lot. And one of our goals for the next 2 years was to put together a workshop and bring people together to talk about a number of these issues. So we wrote a grant proposal, and it was funded by NASA. It was supposed to take place in the summer of 2020, which obviously that didn't occur. We are tentatively setting it for June of 2021. We'll see. We're not sure that's even going to happen, but the goal of this workshop will be to build a global scale validation network, and the workshop will cover a number of aspects, including the standardization of protocols, what are the instrumentation needs, what's currently going on in the validation world, what are the validation metrics, what metrics or statistics do we need, are standardized, that we can use across these projects and operational efforts. And in this project, this workshop will bring experts together from both the remote sensing and the in situ observational community. The last project I'd like to talk about is what we're kind of excited about, which is just kicking off, is the development of a knowledge hub. We see this as a capacity building or training effort. Essentially, we're trying to build a web-based resource where we can kind of compile all the tools, documentation. Again, this is to empower people to be able to do this work themselves. We see this, as it says, this would be a place where people from around the globe can come to work on this subject matter, exchange ideas, experiences, and increase one's expertise. It'll hold resources such as listed here in the table, publications, code models tools, remote sensing imagery data, or point to it, the in situ data, results and products of previous work, and a number of other things. Again, such as a place where people can exchange their experiences and ideas. So we don't have funding for this. This has essentially been an ad hoc effort. We've just had conversations about it, and we are seeking funding or support for this effort. So in summary, water quality continues to be a critical issue globally. There's multiple streams of water quality data, as you've heard here and in other talks today. that are being generated on a near daily basis now. AquaWatch provides an important platform and forum at this critical time to address some of the data quality needs. And AquaWatch is involved in many activities to support developing a water quality information service. So with that, I'll quit. If any of you are interested in joining one of our working groups or just understanding more about AquaWatch, please contact Mary Beth Neely, who's our AquaWatch Secretariat, or myself, and I'd love to talk with you about some of the AquaWatch activities or your particular needs or how you can contribute to our efforts. We do have an website, geoaquawatch.org. So with that, I'll quit. Thank you.
Thank you very much, Steve. That was a really interesting introduction to GeoAquaWatch, and I was especially interested to hear the bit at the end about the Knowledge Hub. That would be an absolutely brilliant resource. I hope you do get funding for it. And I just thought I'd mention it because I know one of the questions that's come in for our discussion panel in the next session is about how can we facilitate knowledge sharing and take forward what's starting with this, with all of these projects we've heard about. And I think we might want to come back and hear more about that. I'm going to hand over now to Tiago Silva from CFAS, who's going to talk to us now about data cubes.
Okay, thanks for having me. So we've heard quite some interesting talks on science and non-application. I'm going to be talking about on the tool set side of things, how to bring these things together. So these are mostly results from a Horizon 2020 project with a number of European partners, where we've been using a tool called Xcube. So it's an open source DataCube server that was partially developed in this project. So I'll start with what is a DataCube for the ones that haven't heard about it. List some advantages, how does it work out for water quality, and finally some very brief examples of data cubes we developed at CFAS for particular applications in water quality. So first of all, a data cube is at the center of it. It's a data repository on a shared grid. So we can think of it for, say, for an array of water quality sensors in the water. For instance, in depth, we can think of that as having two dimensions, a grid with 2 dimensions: time, we're recording a time series, and location, for instance, depth or reach along a river. Or for satellite imagery, you can think of latitude, longitude, or 2 spatial dimensions plus a 3rd dimension of time. Or even further, for, say, a 3D ocean model, we can add a 3rd dimension of depth together with time and space. So we've got a number of different variables brought together on the shared grid. And dimensions, each variable can be a different set of dimensions there. And the crucial idea here is that we can apply our operations, say, for instance, an average, equally over any dimension using the same operators, using the same ease, and aiming to have the same performance. While before we used to working with a stack of satellite images, which it's okay for loading individual images and it can be fairly fast. But the moment we start looking at over time, then we can have to address them differently programmatically, and it becomes much slower normally. So it's an attempt to bring all these dimensions to be explored with the same ease. Motivation on one side with data size growth on this image on the right, this plot from DLR, the German space agency, shows their estimates of predictions of space data storage until 2030, and we can see that it's a wealth of data becoming available, but we're past the point we can just download images to our machines and process them. So we've got to look for tools that make it easier to make the most of the data. And also, as you'll see, a complete data cube will have also the tools to use the data. So it's not just about making the data available, but it's pairing that with tools that allows us to explore it properly. And finally, reproducibility of science, as was highlighted in 2017 with Nobel Prize for Physics, with gravitational waves. And very soon after those results were published, there was a Jupyter notebook that was interactive, that allowed people to reprocess some of the data and learn about the algorithms, the complex algorithms that were being used. So by having an end-to-end tool that does all the processing of data, makes it easier to reproduce, doesn't require installing and understanding all these different environments for each tool that make up the workflow. So I've got a little diagram here of trying to help us choose if we could benefit from having using a data cube. The first condition here is a necessary condition. Is your data gridded, for instance, time series, images, etc. But if you reply positively to 2 of these 4 questions, I would say should really be considering data cubes. So is your data set too large for running on a PC or a VM? Does the data require an automated pre-processing? You might have daily images being pulled in every day and you want to add that to your time series automatically. Are you doing a number of steps to generate analysis ready data? Is the data being used by more than one person? Eventually, maybe even public access, lots of different people. And finally, do you need a web viewer to go with that or to analyze, to allow you to map, to produce time series, to do statistics over time or space? So an anatomy of a data cube service, you have at the center of it the storage of gridded data in a format that allows it to work efficiently, something like ZAR or HDF cloud that can be parallelized, can work quickly on the cloud. And you have the step of going from images, say NetCDF or GeoTIFF images, and doing the ARD processing until it's gridded. And then you add a server to it and an API. Typically, you have most data cubes provide a Python API, but others are available that allow you to query that data cube and do data analysis. But if you pair it up with a web server, then you have a number of other possibilities. You can, using any web browser on any device, you can do data querying or a certain level of analysis without installing any particular tools. And also, if you have a web API for data, that means you can do analysis in a way that it's agnostic in terms of the tools you're using. You can use R or other languages to query data over in the web API, pull in a time series, and then you'll do your customized analysis locally. So you can have many users and even different use cases, different applications for one data set. So looking at some data cube usages in the marine domain, the fulcral thing here is that by having great ease at analyzing over time and space, that allows you a number of new things. For instance, if you're looking intertidal cycle or coastline change, that's made easy by that possibility. For instance, for the Digital Earth Australia, the Australian Data Cube, they produced intertidal DMs in an automated way by analyzing many images at different stages of the tide and pairing that up with a tidal elevation model, and they could generate that automatically without any operator intervention. It also helps with deal with clouds, with other sources of missing data to generate other mosaics or have more robust statistics by aggregating over space and time. And the same for area statistics. For instance, if you're doing environmental assessment for a certain region, or for doing classification of processes changing over time, for instance, river plume. It can also allow you to experiment and very cheaply have a number of different products or algorithms by calculating them on the fly. So you can add an unlimited number of multi-band indexes because you've got all your variables, for instance, your reflectances stacked up on the same grid, and you can combine even between different sensors to generate new algorithms, new products if you want. So this is thinking of pixels as independent observations, certainly with some correlation in space and time, but by pulling them in space and time, you can reduce uncertainty, you can combine them to increase your accuracy. So should we have general data cubes that, as in the Australian data cube example, that cover a whole continent, a whole country, maybe even larger? or do you need specific data cubes? Well, it depends on the case, of course. In the marine domain, there'll be some specificities. Well, starting with grid, it of course depends on grid choice and coverage. If you're working with a high resolution grid, it will be expensive to have a very large coverage. So it might be that you want a high resolution grid for your small coverage area of interest. But also, you might have chosen a specific atmospheric correction for your location. It works well for the region you're looking at, and ocean color scientists spend an inordinate amount of time comparing different atmospheric corrections for what they're interested, for the particular features of the spectrum or the bands they're interested. So you might have to choose something that works well for that case. And even more so for biophysical parameters you're trying to estimate. Even for just one particular parameter, it might be that for different ranges of values, you want to have different fit or different algorithm. So by building a specific data cube for our application, you have the flexibility to do so. So some quick examples of water quality data cubes we've built at CFAS to help us explore and collaborate with other people, explore data and collaborate with other people. For MSFD, for Marine Strategy Framework Directive assessment of eutrophication, we've built a data cube that covers UK waters, that uses a coherently, spatially coherent algorithm, chlorophyll algorithm from the UNOSAT project, and also other more general global algorithms to compare with. And we've added a number of spatial layers that we combine with this algorithm. We also have sea surface temperature, for instance, and also vectorial data, such as the COM4 assessment areas for the environmental assessments, the locations of our sampling sites, the smart buoy locations, and this serves the viewer, serves as a tool for assessors to explore data. A much higher resolution data cube we've built for Liverpool Bay. This is for continued work with Environment Agency on their WFT eutrophication assessment, where the turbidity, we use SPM here as a proxy for turbidity, is a limiting factor in eutrophication. So it goes into estimates of eutrophication risk. And here we're using, because WFT water bodies, Water Framework Directive water bodies can be quite small in scale, might be an estuary or a narrow coastal strip. We're using Sentinel-2, 10 meter. The case has been quite well made before by Claire and Stefan on the strong points of Sentinel-2 for these cases. And we're using this to estimate SPM, and we're experimenting with algorithms working on different bands and different algorithms for different ranges of turbidity. We sometimes have very high turbidities in estuaries, and so that requires specialized fits. In this case here for the Ribble, you can see how narrow in the in low tide the river can be 100 meters across. So the high resolution here is quite essential if we want to be able to sample in low tide. We're also adding, alongside with the vector layers of WFT water bodies, we're combining these with the EA water quality data archive. So from the monthly surveys that are being used, and this is part of the aim is to integrate these in situ observations, the monthly surveys, with additional EO data. And here for a more localized application, marine discharges from power stations. We've been working on power stations managed by EDF by using, so these are water cooling marine discharges, although the application also exists, can also be applied for sewage discharges. But so we have the power station that takes in seawater and uses it for cooling of the power station and pushes it out again. So that is quite an obvious signature if you're using high resolution sea surface temperature. So this is Landsat 8, 100-meter resolution, atmospherically corrected with several algorithms. And as you see here on the right, for Sizewell Power Station, there's this darker blob of hot water that is coming out of the outfall. We are combining this information with the geographical information of the intakes and outfalls of the power station, and also polygons of protected areas for monitoring application. And on top of that, we're putting automatic detection of the plume where the temperature is above the background to be able to estimate areas, etc. And in situ SST from WaveNet sensors. So I'll finish with this little mosaic of other well-established DataCube softwares out there, and some of the big projects have been applied. So as I pointed out, we've been working this. Our experience was with Xcube, that is now being used on a big project, EuroDataCube, that is aimed at generating DataCubes on request. But other quite well-established DataCubes are around, as you can see here. That's all from me.
Okay, thank you very much, Tiago. That was a really interesting presentation, a good introduction to the subject. Very interesting to me because we at JNCC are working on a DataCube project for terrestrial applications that's funded by the DEFRA Earth Observation Centre of Excellence. And yeah, it's really, really interesting to hear about some marine applications. I can see that there's a lot more besides the examples you gave us as well. That's amazing. We're now going to hear from Andrew Tyler from University of Stirling again. So thank you very much to Andrew for agreeing to do 2 talks in one afternoon. Really appreciate that. And now we're going to hear about the living laboratory prototype for Forth Valley. So over to you, Andrew.
Well, we started this today's session looking at the global scale, and now we're going to come down to a little bit more the local scale and how we can exploit this capability locally, really to promote the economy. So and our recovery, if you like, from both the COVID period, but also in response to that green recovery that we all now have as a target to deliver on that net zero target by 2045 in terms of Scottish targets at least. So what we're doing is building a living laboratory, and at the heart of that living laboratory is what we're calling the Forth era, because it's based on the Forth catchment. And this is really combining satellite data with in situ data and also modeling to provide an information flow to inform behavior, essentially, and change. So just a bit of a backstory to this. This really comes out of a new development called Scotland's International Environment Centre. A little bit of a mouthful, so I won't say that again. And this has been funded through the Stirling and Clackmannanshire City and Region deal, which has provided a £22 million investment in this new centre, which really is being designed to really reimagine how we do this environment thing, really promote innovation and business development in a way which supports the environment rather than in a combative way. So this is a really, really exciting opportunity and development that we have. And it is really about breaking down those traditional disciplinary silos, institutional silos, as well as sectoral silos as well, to bring people around the table to really unlock what's those seemingly intractable challenges, really, be they on the local level or be they on the global scale, and ultimately that climate challenge and responding to the climate emergency. And this came out really from following a series of discussions with senior ministers, both in Westminster and also in Holyrood. So as I said, it's a very exciting development. And in a little bit more detail, it encompasses the development of both the Research and Policy Centre, which includes a safe space, a collaboratory, if you like, which includes a decision theatre, where we can bring in data to help inform decisions and better decision making. It also includes a test and demonstration centre based on the banks of the Forth, and also fundamentally important is also that skills training capability, both in that digital space as well as the environmental space. And that's those skills to build businesses, entrepreneurship and enterprise skills as well. And to go alongside that, there's also a business innovation incubation centre as well. So I say a really exciting opportunity. This has been several years in the making, I should hasten to add, and I'm sure those of us in the UK can imagine some of the delays to actually getting this deal signed, actually, particularly in 2019, through both the general election and Brexit. But fortunately, the deal was signed in February this year, just before obviously the outbreak of the pandemic. So, as I said, the core of this is building a living laboratory, and given the changes that we've seen and the pressures that we've seen over the recent months to really try and drive the economy forward, we've also developed the concept further, and that is to deliver a platform to help that recovery, that economic recovery. And so we're building this as really Scotland's first regional recovery platform. And what we're doing here is really bringing together data sets for the whole of this catchment, both obviously existing data sets, but critically real live streams of data sets from sensors from existing platforms, augmented also with new sensors, which are also in response to the needs of the business community or the regulatory community and so on, depending on what the challenges and the needs are. And coupling this, obviously, with Earth observation data to give us that spatial perspective, and also real-time analytics as well in terms of modeling as well. Ultimately, that is to obviously, from our perspective, to drive forward world-leading research, but also, importantly, innovation opportunity as well, particularly at that sort of regional scale. So all of this information should hopefully also promote better environmental management and regulation, but as I said, also stimulate business innovation as well, and basically target that net transition, that just transition to a net zero carbon economy in particular. Now, to do this, we have to work across all sectors, and we have been in active discussions, a huge amount of work across a whole range of industries and statutory agencies, for example, which I've listed here, to truly tackle some of those key challenges that we have, not just at the global scale, but clearly also at the local scale. Now, what we're doing at the moment in these early phases is really building and demonstrating. And as if you look at the logos at the bottom here, you can see that the focus is very much on the water sector, supported by industry, and in particular by the Forth Valley Chamber of Commerce, who realise that basically that transition has to be led by commerce, because that's where the money is, and they need to see the opportunity for business development, along with Scottish Water and also a distillery Diageo, and again with the statutory agencies SEPA and also Nature Scot, formerly SNH, as well as a community body which is bringing all these organisations together, the Forth Estuary Forum. So why water? Well, I think hopefully we all understand water, but and if you didn't, really appreciate it, as quoted by the UN, water is the primary medium through which we will feel the effects of climate change if we haven't realized that already. So that materializes itself in terms of extreme events such as floods and drought, but also deteriorations in water quality. And all these factors have non-linear and very complex interactions with both the biodiversity in the environment, but also ability to trap carbon in the environment. And actually in the UK, we have about 80%, for example, of our peatlands are in a degraded state. And rather than actually trapping carbon, they're actually contributing quite a significant amount to the UK's carbon budget. There's a real need to remanage those and to rethink how we use those landscapes. All of this has an impact on the economy and also to the security of assets that we all become to rely on, both in terms of shipping as well as energy, water, etc. So it is really fundamental in terms of the economy going forward, as I think we all fully appreciate. So in Scotland, at least, and perhaps in contrast to popular opinion, it's not necessarily getting wetter as a result of climate change, but what we are seeing are significant shifts in the way that delivery is occurring, that water delivery is occurring. So what we're seeing is more intense rainfall events separated by longer periods of drought, essentially. Now, if you think about those intense periods of rainfall, that is also leading to more issues occurring in the environment in terms of flooding. And we've also seen issues around the rail transport as well recently, accidents in Scotland, particularly on the East Coast. So it is providing us with serious challenges, and clearly flooding in the catchment coupled with storm surges coming from sea, that then also really brings real challenges to the assets that we have, the commercial assets that we have in these environments, many of which we are fundamentally reliant on. But it's not all doom and gloom. these environments, the water environments, the whole of the catchment, also provide us with real opportunities to drive that green recovery, be it in terms of new ways of generating energy, in terms of thermal extraction of heat from water, or indeed kinetic energy extraction of heat, but also ways of also reimagining the landscape, or encouraging the landscape also to trap that carbon away. So really thinking about re-wetting our peatlands, for example, to make sure they are acquiring carbon and not releasing carbon, as well as other wetlands as well. So they are very real opportunities. But to deliver on this really needs a new level of observation beyond what's currently available. Now, obviously, we've been talking about Earth observation in detail, and clearly we've got the capability, and we can tune that capability locally, as has been described, to deliver really good values of water quality in particular. And we can also look at water quantity, particularly using synthetic aperture radar data. And here we have just a quick snapshot of the fourth catchment, the fourth estuary catchment, or fourth catchment as a whole. So you can see both the estuary itself, the transitional environment, but also the different water bodies, the different lochs and reservoirs that we can image from space. And this is Sentinel-2, that's back at the, I think it's 28th of May this year. Couple that data also with, this is data from Copernicus Land Service, estimating soil moisture concentration. Now this is using SAR band C data, which is perhaps not optimal for water moisture estimation. I think L-band SAR is much better for that, and we're obviously waiting for that capability to come forth. But nevertheless, actually, this data does give us quite a lot of interesting information. You can see that this is actually at the end of a long period of drought, actually, in Scotland. And so we do have low water concentrations in soils where we'd anticipate them, and slightly higher in the organic soils in the upland environments and the lowland mosses as well that we have in the catchment. So we can grab data and process data at a spatial scale, which gives us really important spatial data. But it's obviously only at snapshots in time, be it daily or every few days and so on. But these are really dynamic environments. And we need to couple that data with sensor data. And here, for example, we're grabbing data from the Superbuoys and the Superbuoy network that we have. And that includes both water quality, as indicated here, but also water quantity from staging gauge stations in the catchment. We also take data from, this is the Centre Ecology and Hydrology Cosmos station for looking at soil moisture. In addition, we're also in discussions with Forthports, who have a number of assets and buoys within the estuary, which are also partly instrumented, which also can provide information which could feed really valuably into models. So here we have then data, which we will also add to that data in terms of in situ sensors to, say, plug some of the gaps that we have, both in terms of what's being monitored and also where it's being monitored in particular. But fundamentally, we still have a space-time gap. And that's where the modeling comes in, basically, to use this data to feed models in particular. So the platform then, in a little bit more detail, is basically then capturing data from satellites, augmenting that with in situ sensor data, partly to validate the satellite data or help the calibrations for that satellite data, but also for measuring in-water constituents, both of those which are optically active, which we can measure from space, and those that aren't, such as nutrients or metals or whatever else is we're interested in looking at. We also have the capabilities we've also demonstrated for looking at the optically active in-water constituents and characterizing that environment in particular, but there are also new ways of sampling the environment, particularly beyond what is normally observable. We're looking at bed load sediment transport, and we have the capability working with partners, other SMEs in particular, for putting flumes on the bed of the estuaries so that we can understand sediment bed load transport as well. So here we have data which we now can capture spatially and temporally, and the program going forward is now to incorporate that data into modeling, so we can exploit so that machine learning capability, the AI capability, if you like, to fill some of that space-time gap. But where processes are particularly important, and also we need to bring in hydrodynamic modeling as well, and that then gives us that capability for nowcasting to fill the gaps in terms of what's happening between sensors or between Earth observation image acquisitions, but also critically forecasting, so we can think about what-if scenarios. Now that's all well and good. So we can generate data, we can generate models. And I say that almost flippantly because there is a lot of work that needs to be done behind this. But from here, this point onwards, what we need to do is transfer or transform that data into evidence, into knowledge that can then affect and change behavior or better practices in the environment. And we're working, as previously mentioned, also with 3DEO, which is a data visualization company that really are bringing in novel ways of actually presenting data and also exploiting AR, augmented reality type technologies, either through smartphones or through goggles, for example, so that we can bring that data both to the community level, but also to business level, so that we can help people to visualize the environment, what's happening to the environment, the consequences of behavior, the consequences of different types of mitigation measures in particular. So that's the concept. And ultimately, what we're doing here is really taking this as a platform to affect behaviors, drive that transformation at every level. That gives opportunities for innovation. So we've already been approached by a number of sensor companies that would like to try and use this platform also to demonstrate or build their own capability as well. And that also helps us to think about also business innovation opportunities, but also within existing organizations to drive efficiencies in terms of how they, for example, abstract water and then also discharge the waters back into the environment more effectively and minimizing that impact on the environment. Ultimately, what we're trying to do is grow that resilience as well. So this is where BT in particular is of particular interest, and they are our commercial lead on this project, and they're bringing that capability. So we're exploiting the Internet of Things type technologies, LoRaWAN, 4G, but of particular interest is now exploiting that 5G capability, and they're building a digital fabric for the exploitation of that 5G capability across the whole of that catchment. So what we're doing here is now being able to capture sensor data in ways that hitherto hasn't been possible in terms of volumes of data, process it, and then push it back out again to the community, to organizations and so on, so they can affect better behaviors and actually look at the implications of decision making that they are thinking about. Critical here is that co-development. So we're working, as I've said already, in partnership with industry as well as CEPA and Nature Scott, for example, in identifying what is really needed and what the priorities are. So I was hoping to be able to give you a demonstration of what the platform looks like. Unfortunately, given COVID, there's been somewhat delays in the sensor delivery, which are now actually arriving this week. But what we have here on the right is just a mock-up, actually, of some part of the portal that's currently being developed by 3DO. So we're looking here at mock data for examining sensors, for example. But fundamentally what we're doing here is building a web-based platform which brings in data, enables us to process that data and also then push it out in different formats to enable clients, different parts of society essentially to exploit that data and hopefully inform better behavior. We're exploiting that 5G capability to really think about bringing in data in volumes, as I've said already, in ways that hitherto has been really challenging. Process it and push it back out again, really in that near real-time capability. And in ways that again, has hitherto been rather challenging. So exploiting that augmented reality type capability. So, so we're currently developing a concept for this, or a proof of concept for this, based on Loch Leven, where we've done a lot of work already and working in partnership with the Centre of Ecology and Hydrology, and also CEPA in working in this particular catchment, where both organisations have done a lot of work. So I'll explain it briefly in a second. And we're developing a number of use cases in this area. So with Scottish Water, looking at the opportunity for Earth observation for delivering water quality data, as we've discussed already at length. But also water temperature has been hinted at here. So water temperature is a key issue in terms of the brewing industry and distilling in particular. So taking in water and then discharging it at a higher temperature over ambient levels. And that has a regulatory requirement as well. So demonstrating here for Diageo those regulatory requirements and going beyond compliance in particular. but also working with SEPA in terms of bathing water quality. We're putting in a sensor at the bottom of the lever here to measure coliform concentrations, and from that predict E. coli concentrations on beaches to deliver a more informed information on bathing water qualities, essentially, and also reconstruct past flood and drought events, just to demonstrate the art of what's possible. That's what we're working on now. Hopefully have this done by Christmas. Somewhat delayed, as I said, because of COVID and delays in sensors. But then we're also now working with a whole range of organizations that I've already mentioned, just to build this capability and how use this capability to support a whole range of activities in the Forth Valley and help drive efficiencies and reduce carbon emissions, etc. Fundamental to all of this is also carbon mapping and the ability to use this data for peatland restoration, wetland restoration, for example, to promote biodiversity and that carbon capture story as well. I think I'm possibly running out of time. So just to quickly summarize, so this is just a few of the organizations, just to give you a contrast to the sort of organizations we're working with. So 2 weeks ago, Scottish Government announced the launch of Scotland's 5G Centre. I'm pleased to say that the first hub of this 5G centre will be based in Stirling alongside Scotland's International Environment Centre, where we're exploiting 5G particularly for that environment case studies. Also working with innovation centres such as Census, which is around centre development, but also with community groups and action groups as well. So SEPA lead the Loch Leven Partnership Scheme, which really works at the community level to improve the environment and bring the environment into the heart of decision making, as well as working with the commercial sector as well, here led by the Forth Valley Chamber of Commerce, and obviously with regulatory organisations as well, statutory organisations such as NATO Scott. So just to end on, so whilst we're focusing this very much on the Forth in the first place, I should mention something that hasn't really had much of a mention now, and I think Steve might mention it in the next presentation, but we're also leading the UK's input into pan-European infrastructure, looking at river sea systems. This is called Danubius, and by its name you can probably imagine it actually originated in the Danube. But it is now a pan-European infrastructure looking at a whole range of super sites across Europe, as indicated on the map there on the right. PML, along with Stirling, are leading on the observation node, exploiting that satellite and in situ capability, and what I've just described is a potential opportunity for expanding this capability across the whole of Europe. And I should say that also this is now on the S3 roadmap from 2018 onwards, and an application has been made to the European Union for a legal status called an ERIC status, so this becomes a legally binding body, if you like, for Europe, focused on looking at these transitional environments. So I think that's probably enough. So I'll stop there and just leave you with some links.
Thank you very much, Andrew. That was an excellent talk, and really good to see examples of industry as stakeholders and funders of the project. That's really positive. And of course, very nice to be hearing about the Forth Estuary, a transitional water body, because that links in very nicely with our next talk from Steve Groom, who's going to tell us now about the CERTO project, harmonising water quality from oceans to freshwater through these transitional water bodies. So thank you, and we'll take questions at the end of Steve's talk.
Well, I'd like to thank Paula for inviting me to talk at the end of the day, and also thank all the audience who have managed to make it to the end of the day after the longest session. So I'd like to talk about a new project that started this year called CERTO, Copernicus Evolution Research for Harmonised and Transitional Water Observation. Now, CERTO means in Portuguese and Italian correct or right or okay, so we think it's an appropriately named project. And what it aims to do is to bring together some of the aspects that we've seen beforehand, from open ocean to coastal to inland water to lagoons type observations of water quality. So if we go back to Carsten's presentation, you recall that Copernicus is this major EU initiative, and it incorporates essentially two components. One is the thematic services, and the other one is the operational satellite series. So there are 6 services We've heard a bit about Copernicus Marine, also land, and a little bit about climate change. And it's interesting to note that those three, climate change, marine, and land, all produce data which we could call watercolor. I'm an ocean color scientist, so I tend to use the word ocean color, whereas technically it should be water, because not just looking at oceans. The various Copernicus services include watercolor for global areas, and this is provided by Copernicus Climate Change and Copernicus Marine. And here the global data is based on the ocean color CCI that Shubha Satyendranath mentioned yesterday. It's important to note that the approach used here to estimate these data is the optical water type approach that was quite nicely explained earlier by Claire. Now, if we look at Copernicus Marine, they undertake regional processing. So here we have the North Atlantic product. There's also Baltic, Black Sea, Mediterranean, and other products. And the approach here is to use regionally tuned algorithms as opposed to the global approach of optical water types. So again, this is a slightly different approach. Then if we go to Copernicus Land, as was mentioned a little bit earlier by Stefan amongst others, here we are looking at lakes, and the approach here is back to the optical water type approach. But the important thing is that each of these services uses slightly different approaches at different algorithms and arguably different optical water type sets. And perhaps even more importantly is that some areas, are not really covered by any service, such as estuaries, lagoons, large rivers. And these are of particular interest to, for example, the Genubius project that Andrew just mentioned. So these are not covered by any of the Copernicus services. And this can be seen or summarized in this figure here, that you have C3S producing ocean data, CMEMS ocean regional data, Copernicus Land produces lakes, but no one really covers at the moment estuaries, rivers, very near coasts and lagoons. So there's a clear gap there in data provision. So this is where CERTO comes in. So there was a call a few years ago, which we responded to, and luckily got our project funded. So it's a €3 million project, started in January, going on to the end of December 2022. And it has 9 partners led by PML, but it includes Brotman Consult and University of Stirling. So you can see with a figure at the bottom where we hope to be, or where we hope to get to, from the current position where we have 3 services all producing water quality data, and going to a position where essentially we have one prototype, one system that can be plugged into each of the 3 services, providing harmonized water quality products in the entire continuity or continuum between the ocean, regional seas, transitional waters and lakes. So the way we're going to do that is to try and harmonize between the different Copernicus service approaches, and this then feeds down into the research that we're going to do and how this fits into different work packages. So work package 3, 4 and 5 essentially are looking at in-water algorithms, the optical water type approach, atmospheric correction methods. Indeed, someone mentioned earlier, I think it was Tiago, who said that watercolor scientists spend a lot of their time validating and looking at different algorithms for atmospheric correction. This is because really at the moment we don't have one atmospheric correction that really works across all waters. So that's something we're going to look at in work package 3 to 5. In work package 6, we're going to be looking at indicators relevant to management, policy and science users, primarily operating in transitional waters. But the idea is that these indicators could also be applied for lakes and also coastal and possibly ocean waters as well. We're also going to interact and consult with commercial, industrial, policy and science users, the monitoring bodies as well. And finally, the aim is to produce the prototype system, which will eventually be used by the Copernicus services, but also evidence of its value, i.e. we want to show that it is actually worth incorporating into those services. Excuse me. So we have an advisory board. I really show this because it shows linkages with, for example, GeoAquaWatch that Steve talked about earlier, GeoBlue Planet, some people are familiar with, and Future Earth Coast, which is the overseeing body on the Lagoons for Life project. Also has a link with JNCC through Guao, who is on our advisory board. And also we have a link with the Association of Remote Sensing Companies in Europe, EISC, and also with a science user at HZG in Germany. So going on to some of the science activities, this is really going to be focused in 6 transitional waters. We have 3 estuaries and 3 lagoons. So going from top right, we're looking in the Curonian Lagoon in Lithuania, the Sino-Razom Lagoon in Romania, then the Venice Lagoon in Italy, the Tagus Estuary in Portugal, Plymouth Sound in the UK, and the Elbe Estuary in Germany. Now, you've heard about some of these estuaries and lagoons earlier with some of the other presentations. As you can see, they're appropriately politically spread around Europe, but also cover a diversity of different environments. The aim of these case studies is that we're going to take in situ measurements using radiometers, so that's the light coming out of the water, as well as biooptical data, and this addresses the general opacity or lack of data for such transitional waters. For 2 of the sites in Romania and Portugal, we're actually going to purchase some new radiometers, which will be permanently located in those 2 sites and should provide data through the project and hopefully beyond. Also, these 6 areas provide the exemplars for interaction with local and regional users. So we have about 20 or so entities ranging from individual companies up to national monitoring bodies that have interest in these particular transitional waters, and they have been consulted in terms of areas of interest and what data they might want, and they'll be consulted throughout the project. The other areas that we're looking at are the 6 regional, or actually 5 plus combined, regional areas of Copernicus Marine. So that's the Atlantic, Arctic, Baltic, Mediterranean and Black Sea. And also we're linking with global interest through GEO, as I mentioned earlier, Lagoons for Life and the Danubius RI project. Indeed, the focus on transitional waters was to a degree motivated by the needs of this Danubius research infrastructure, which essentially, when we were trying to find out what data were available from Copernicus, found there's actually a distinct lack. So moving on to work package 4 and some of the science. So the first thing we're going to try and do is come up with an optical water type scheme for cross-domain classification. Now, a question was mentioned earlier about whether 13 water types are enough to cover the diversity of global water types. I think this will show that probably there isn't, because purely for the ocean and shelf waters, we have 15 different water classes. And you can see that the water classes here are actually quite different from the ones in inland water. They're primarily focused for open ocean, so-called clear waters, typically just with chlorophyll and associated byproducts. As well, we're going to be coming up with optical water class sets from Sentinel-2 and Sentinel-3. And you heard from Claire's talk about how the different bands will mean that the optical water type sets or class sets will be different between different sensors. And we're also aiming to propagate information on the quality of each pixel, in other words, the uncertainty of each pixel based on this classification. This is an example from the CCI project, and you can see that for each water class, there is a separate estimate of uncertainty here measured as RMSD in log chlorophyll. And you can see some water classes, like open ocean ones, actually have lower uncertainty, whereas as you go to more coastal ones, you can see the uncertainty is much higher. So what we aim to do is, once we've got these water classes, is then to classify each pixel in terms of whether it's, say, 50% water class 1 and 50% water class 3, and then combine the uncertainties to give a per pixel uncertainty in the final product. So moving on to atmospheric correction, the aim here is to evaluate and validate and intercompare the various different atmospheric corrections. Polymer, you've heard mentioned quite a few times, and it's used for lakes, it's used for coastal waters, and also for open ocean. And we're going to trial this against some of the other atmospheric correction algorithms out there. We're also going to look at the adequacy of the water reflectance models that need to be used in coastal waters, because you can't essentially just use the bands themselves to get out the atmospheric components. We're going to look at the impact of adjacency effects, in other words, how close to the coast, which obviously is very important for very near coastal waters, and also look at the bathymetry effect, because actually, many waters are quite clear. Even in moderately murky waters, you still might see down a metre or so down to the bottom. I'm also going to look at the uncertainty propagation scheme for the atmospheric correction. And one of the methods we're going to use is by correlations, by looking at the derived atmospheric components and the in-water components and seeing how in certain blocks they're correlated. Ideally, of course, we'd want no correlation between the atmospheric component and the in-water component because they should be independent. But as you can see from this figure, actually for quite a few points, I think this is the Loire Valley or the Gironde, one of the two, you can actually see that in some places there's very strong correlations. Next, we're going to look at the indicators, and this was one that Shuba mentioned yesterday, looking at chlorophyll phenology, in other words, the timing of chlorophyll peaks when blooms actually happen. So this is a global example. We're also going to look at indicators like this for estuaries and transitional waters as well. And so we've done a user consultation to see which indicators are of most interest. So coming to the end, where do we want to be at the end of the project? Well, we want to produce a prototype that produces watercolour data harmonised across the aquatic environments, hoping to go from ocean to lakes and pretty much everything in between. We want to come up with evidence of the value of the CERTA prototype in these waters, and also to try and ensure that the prototype is actually updated or adopted by the Copernicus services, but also with the indicators and services that we develop within the project. We hope that these will be taken up by the downstream data providers that essentially take data from the upstream providers, the main Copernicus services, and then add value to those products, typically to add new products, but also to meet the specific requirements of local users. So this is essentially where we'd like to end up with this harmonised water quality product set. So penultimate slide, how can you be involved with CERTO? Well, first thing I will do is reiterate the comment that was made earlier by Andrew to contribute your in situ data to the Limnades database. We can only really build our research on taking our own data, but also those data taken by other people in the past, and we'd welcome new data sources going into the database. You can also link to one of the existing user case areas or the Copernicus regional seeds. If you have one of those of particular interest, then do contact us and just say what your interest is, and we'll keep you updated. But also what we're planning to do in year 3 is to add extra regional areas, because in year 3 we're going to produce a pan-European coverage of lots of different areas. So, okay, we've got our 6 areas, but say you're interested in the Thames estuary or the Tay or the Forth, we can also add those areas in. You can specify those areas and we will produce data for those with a time series in year 3. And obviously you can subscribe to the newsletter and visit the website, and I'll just leave you with my email and the contact points for the project. So thanks very much.
Thank you very much, Steve. That was excellent. And we have got time for a few questions. I would like him to take a sorry, it's a bit of echo there. If you could mute yourself.
I will, yeah.
Thanks. Yeah, I think it would be important. If we... Oh, sorry, it's the speakers on your computer. I would like to take a proper break before the discussion session, so we'll just do a couple of questions, Emily, if that's okay, and if our other speakers are available. What's our first question?
Yep, absolutely. So thank you very much, everyone. I'm going to start, if you are available, Steve Greb. Are you there, Steve?
Sure. Can you hear me?
Okay. Yes, perfect. Thank you. So the question that we have for yourself is, the analysis-ready data sounds like it would really reduce barriers to uptake. But given what we've heard about all the different atmospheric correction methods suitable for different sensors and applications, how easy would it be to get a consensus on what constitutes aquatic analysis-ready data?
Excellent question. And I would say our audience is acute in the understanding, getting right to the heart of the issues. What I didn't talk about too much with those 5 or 6 projects that I described was, I didn't get into too much detail about what specifically we're doing in each of those. So with the analysis ready data, I mean, what has prompted our involvement is just what the person who posed this question is suggesting, and that is we're starting to see more and more ARD products being put out there from different agencies, you know, be it USGS here in the States or in Australia. You know, there's folks working on the Sentinel-2 ARD products. And so there is inconsistencies across these ARD products. And they take some different approaches, particularly with respect to atmospheric correction. So we saw this as something that AquaWatch could help or step in on, be it a community effort. So our goal is, just as the question was posed, is, you know, what can we do as a community to try and build consensus and look at some of these, you know, how ARD data is generated, and again, try to come to some agreement or at least some documentation. We're not going to be the algorithm police here, but at least you know, some idea of how that ARD was documented, and maybe we can keep a log of this, if you will, or documentation references on our website, on the AquaWatch website, to describe these different ways that ARD is approached.
Okay, brilliant. Thank you very much. Okay, for the next question, I'm going to go to Tiago. Are you there, Tiago?
Yeah.
Brilliant, thank you. So the question we have for yourself is, how can data cubes be used to analyse sea surface temperature data? Are they being used or considered for CFAS's project of researching hotspots and cold spots? And I know that you did mention in your presentation about plumes coming off of power stations and picking up sea surface temperature with that. So what would you say in terms of the hot and cold spot analysis?
Yeah, thanks. That's a good idea. So that refers to a project funded by DEFRA Center of Excellence for EO, Earth Observation, looking at cold spots and hot spots for fish mortality. And I've been finding that once you've built the data cube, applications appear to that data cube. So even though it starts by being specific, I think for this application, the data cube we've built for eutrophication that includes Ostia SST, so 5 kilometer, 4 kilometer scale, it's more suitable for most cases, I expect. So that's something that has been approached briefly, but I think it's a good idea. We should carry it for further.
Yeah, absolutely. Fantastic, thank you very much. Okie dokie. Now I'm going to go on to Andrew, if you're there, Andrew.
I'm here.
Fantastic. Hello. Okay. The question that I have is actually just one from myself, thinking about this fourth era, and right at the beginning stage when we're looking at spatial and temporal data. You give the 4 examples of data that we're collating to feed through this method, this system, so Earth observation, sensing, sampling, and measurement. Would you say that out of any of those 4, there's one area that is lacking in any way that you would want to see advancements on the information that's coming from that particular area to help? Or do you feel like there's a good data coverage throughout?
Sorry, is that from sensors or from satellites perspective?
That was from all the different data types that you're bringing together. If any
Well,
one of them is
I should say that we are very much, and I probably didn't emphasize it, very at the start. As I said, the deal has only really just been signed, and now we're putting just a demonstrator together. What's missing is probably sufficient in situ data to help partly the validation, but also providing that time series data so we can predict what's going on between satellite observations. I think that's a key area, and I see it's actually one of the areas that's picked up in one of the questions for discussion later. So that's really important. Clearly, there's development that needs to be done on the different areas of satellite data provision. For example, soil moisture as well. I think that was a subject of your previous workshop. So there's real opportunities there. But even there, the data does look quite reasonable, at least from a provisional look at it. A more detailed answer to that question, I think, will come as we address the specific needs of different end users, in particular, as we build this platform going forward.
Okay, fantastic. Thank you. now going to go on to Steve Groom, if you're there, Steve.
Yep.
Fantastic. So the question we have for yourself is it feasible / desirable to group transitional waters into optical water types, as has been already described earlier for lakes? Or is that not possible in transitional waters? Are they too different and dynamic?
My feeling is it's, I don't know about desirable, but I think it's feasible. My gut feeling is that the range of water types will probably be similar to lakes. I mean, lakes are such a very wide range of environments in terms of chlorophyll, in terms of depth, in terms of bottom type, clarity, things like that. So I think it probably is. It is feasible, and certainly that's something we're going to try in Certo. So maybe report back in 2 or 3 years' time to let you know whether it's worked. But, so I would say yes, I think it is feasible. Desirable, not very much so, I would say.
Yeah, there's always got to be some nice to haves. Yeah, absolutely. Paula, how are we doing for time? Have we got time for some more questions?
That's been, I think it would be better if we do take a proper break this time, because we did go over into the last two. And in response to what some people have been asking me in the chat, any questions that we don't get to, they're all stored and captured digitally, and we are going to circulate those to speakers to give them the opportunity, at least, I don't know if they'll have time, but I hope that they have the opportunity to reply in writing to all of the questions that came to them, and then we'll put that in the report that we'll write of the workshop, and that will be publicly available on our website, because there have been some really fantastic questions coming in and speakers have commented on this. So what we're going to do now is take an actual break, and we will come back at 20 to 5 for our discussion session on innovation through to impact. During the break, you can also have a look on Meeting Pulse and see the suggestions that have come in and the questions that have been asked. If you want to put any more questions to our discussion panel, of course, you can still do so during the break and during that session. So we'll see you back at 20 to 5. Okay, thank you.